Now, I'm not 100% sure why first order ODEs applications include compound interest. Well, I kind of do, so I'm going to try to get there. So don't turn this off because we're going to get to something that's related. So if you've had any kind of class that talks about exponents, at some point you probably saw a formula that looked like this. So the idea was that this here is your current amount of money. This was your initial investment. R is your percent interest rate, annual percent interest rate. And N is your number of compounding periods. So say that it's like compounding like monthly, then that would be 12. And then T is the number of years that it's compounded, number of years. So the idea was that if you had, I don't know, like if you had $500 in a bank, your initial deposit was $500 that in a bank that pays, say, 10% for, and usually is going to say like compounded monthly for, I don't know, 6 years. What do you end up with? Okay. So the idea is, if you want to know what your current money is going to be, or your money is going to be after all this time, you would say, okay, well, I invested $500 plus, and then your rate is 10%. But the thing is, like, you don't get 10% per month. You get 10% eventually. So what they do is they divide the 0.1 divided by 12, but they do that 12 times for every 6 years. So the idea is that you would come in here and you'd say it's 500 times 1 plus 0.1 over 12, and that's going to be raised to the 12 times 6 power, like that. And it's going to say, oh, you end up with $909, and you're like, yay! Alright, so that's kind of like a standard compound interest problem. Now, where this is kind of interesting is that you've got another way that you can do this, which is called compounding continuously. And this is kind of cool. So the idea was, say you put money into a bank and you constantly got a rate of R%, or say you constantly got a rate of R. So that would mean that your change in your money would be a constant based on the current value. So we've kind of seen that before. So your rate of change is directly proportional to how much money you have, but it's not just something that's happening once or twice. It's actually compounding continuously. So that means now we know that the standard form of this is going to be that Q is going to be equal to some constant times e to the integral rdt. So that means that Q is going to be equal to C e to the RT. And at t equals 0, we'll say Q equals Q naught. So whenever we plug all that in, we get that Q is equal to Q naught times e to the RT. All right, so this is continuous compounding. And you're like, okay, so if I make money that's compounded continuously, I just put in the rate. There's nothing to divide by because I'm constantly getting some weird rate and blah, blah, blah. But why do I care? I don't really know if this is why we specifically care, but this is something that I think is really cool. So this is my original equation if I'm compounding at certain periods, as I have Q 1 plus R over N to the NT. Now, if I have an infinite number of compounding periods, so I'm going to write this down because it's important. So if I have an infinite number of compounding periods, that's almost like having it go continuously. Or not almost like, that is. That's continuous compounding. So I could say, what if I take the limit? If I take the limit as n approaches infinity of this, then that should equal Q naught e to the RT. Should. or it does. No, I'm going to say does. Should. It does. So as I take an infinite number of compounding periods, that needs to equal the other side. So I'm going to just go ahead and work here on the left. If I want to, I can pull the q out, right? I can pull the q out on the left, and if I pull the q naught out, because it's just a constant, in fact, I'll just erase it. I can divide both sides by 1 over q naught, and that's not affected by the limit. But basically what I get is that the limit as n approaches infinity of 1 over r plus n to the nt is equal to e to the rt, like that, which is kind of cool. I can also take the teeth root of both sides, because that has nothing to do with n either. Just doesn't. So then I get that the limit as n approaches infinity of 1 plus r over n is equal to e to the r. Now that's really cool, because that's actually some kind of definition or something really cool to know about e. And if I let r equal 1, so if I have a rate of 1, then I also get another definition of e, that's that the limit as n approaches infinity of 1 over 1 plus n is actually equal to e. So that's a really kind of a cool definition, and I don't know where else you see the derivation. I always just saw that as a definition of, like, here's something we know about e, and I'd be like, why? And they're like, I don't know, just shut up and quit asking questions. And so this is kind of cool, because it's actually a definition-ish kind of thing of e, and one of the ways that you can identify it is through looking at compound interest, continuous interest, and stuff like that. So it's actually pretty kind of fun.